Hello and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and my guest today is a Schmidt Science Fellow at Stanford. So I first met this guest at the Conference on Decision and Control last year. She spoke in the workshop on control architecture and I was absolutely blown away by her work. She very kindly recorded a very small snippet about her research whilst we were at CDC. But I was desperate to get a full-length interview with her because there are so many cool elements of her research. So essentially, her work has two strands, one related to model predictive control and the other being control for AI. So I've decided to split these up. So this episode is just going to focus on MPC. You're going to have to wait a little while for the AI control episode, but I promise it will be worth it. So buckle up and get ready to hear all about distributed and localized MPC, system level synthesis, ADMM, leveraging system constraints for parallel computation, as well as the importance of internships and outreach with my guest this month, Dr. Carmen Amo Alonso.
My name is Carmen Amo Alonso. I'm currently a Schmidt Science Fellowship doing my postdoc at Stanford, and I'll be an incoming assistant professor at UC Berkeley in 2027.
So the first question that I usually ask everyone they interview is how they got into control. So I saw that you did an undergrad / master's in kind of aeronautical space engineering. So how did you transition from that into your PhD in work now?
Yeah, when I started grad school, I was really excited to do more space stuff, and I applied to Caltech, and I got in because I was really excited to have some connection with JPL.
So JPL is the Jet Propulsion Laboratory, which is owned by NASA but managed by Caltech. It's involved in a bunch of very cool space-related projects, including building the Mars rovers Curiosity and Perseverance.
And I started doing my master's in aerospace engineering, and we had one elective. And for this elective, I took control because everybody was talking about this class being taught by John Doyle and how he was balancing poles and doing all these experiments in the class or whatever. So in the most random way, I was in a concert and I sat next to another grad student. He started telling me about this class and I became really curious. So I went to this class and I didn't know anything about control. And I went to this class and I thought it was fascinating. And then I remember John started talking about bacteria and how control applied to bacteria and all these things. And I was like, wow, this is much cooler than just like planes flying. Like this explains so many other systems. And so I switched into the program for control at Caltech, which is called CDS. And then the rest is history.
So I've added some links below to papers by John Doyle that examine the role of internal feedback pathways in biology. So in particular, these papers look at how this type of feedback allows biological systems to work optimally when using very diverse components. So, for example, there's a well-known concept in biology called the speed-accuracy trade-off that basically means that biological sensors can be slow but accurate or fast but inaccurate, but generally you can't get both. So one example of this would be that vision is slower but more accurate than proprioception. And the papers by John Doyle use tools from robust and optimal control theory to understand how this works and how you can get optimal systems within the architecture of biology. So moving on to your PhD work now. So the title of your thesis was Distributed and Localized Model Predictive Control. So in terms of general motivation, why is designing a distributed MPC controller important and why is it beneficial for it to be localized?
Yeah, so a lot of systems in nature have distributed computation and distributed control. Like, for example, the brain, there's not one part of the brain that is controlling the rest. And this happens in many systems in nature too. Like if we think about a community of bacteria, it's not like there is one godlike controller that controls how everything behaves in this network. Same thing with a fleet of autonomous vehicles, or even in the powered network. You wouldn't want to have a controller localized, put in somewhere. You want to distribute this computation across different systems because that enables for parallelization too. So then things are scalable. Once you can parallelize the computations, then you can plug and play. Like you can plug in more systems and still have the same computational overhead because things are running in parallel. So that's the benefits of distribution. But what I said about parallelization and about scalability is only true if you can only talk to your neighbors. If you have to talk to everybody, then the more agents you have, the more computation and the more information you have to process. So that is why localization and distribution kind of go hand in hand to make systems scalable and have parallel computations.
So, what are some of the challenges associated with kind of both distributed MPC controllers and also imposing the locality constraints that you talked about?
Yeah, so I think something that was overlooked in the literature by the time I started doing my research, and it was even seen as a challenge, is the fact that in large-scale networks, the couplings are often sparse, meaning it's actually hard for every subsystem to communicate with every other subsystem in the network. And so when you don't have this global communication structure, porting over the standard techniques from centralized control was hard, and that was seen as a challenge. So what we did instead for my thesis was we turned that around and we said, no, no, no. Actually, the fact that you can only communicate to your neighbors is an advantage. Because that way, you only care about what your neighbor is doing. And if something is being plugged in the network somewhere like far from you, you don't need to care. And so we took advantage of this localization, and this is what enabled the scalability. Now, capturing these constraints, like there's a mathematical way of writing what it means for these policies to be localized, and writing that down and putting it into an optimization problem turns the problem into a hard problem. Like it's not trivial to solve that. But we leverage the system synthesis parametrization, where putting these constraints is very natural, and so everything followed very nicely. But in principle, if you didn't have that parametrization, it wouldn't be clear how you would be tackling this constraint mathematically, if that makes sense.
This system level synthesis, or SLS parameterization, is something that we're going to come back to a little later on. But first, I want to give a general overview of this framework. So, Carmen's distributed and localized MPC framework is applied to interconnected systems modelled as directed graphs. And the idea is that instead of using one big MPC controller, you use a bunch of subcontrollers that have communication constraints or locality constraints placed on them. And the specific definition of localization that Carmen used in her thesis related to something called D-local information exchange. And this essentially means that each MPC subcontroller within the network is restricted to only using information from controllers that are D number of hops away from it. Also, I wanted to mention here that Carmen's PhD work in this area won the Caltech PhD Dissertation of the Year award, and the paper that she published on this topic in Transactions on Control of Network Systems won the IEEE Best Paper Award. I've included links below, would highly recommend giving that paper a read. It is super interesting, very well written. Go check it out. I guess kind of going into more of the technical details now. So one thing I was really curious about is the difference between open and closed loop MPC, because before reading your thesis, I kind of just assumed that all MPC was closed loop. But it seems like this isn't the case. So could you explain what the difference is and why you might use one over the other?
Yeah, so in my work, we refer to open loop MPC when you're solving directly for the control input. So your optimization variable is the U that then you plug into your system. And we call it closed loop when we're solving over policies as opposed to inputs. So here you're solving, so for example, you're computing the K, or you're computing like a function, and you're solving the optimization problem over that class of functions as opposed to just some vector variable input. So in our case, we parameterize the class of functions with the SLS parameterization, and that's why we call it closed loop.
Does that have links with reinforcement learning, or is that not a good way of thinking about it?
So we haven't explored those links. Even in the data-driven case where we don't rely on a model, I think the framework would still be different from standard RL. Okay. Yeah, but we haven't fully explored the links.
So, another key concept which you have mentioned already was system level synthesis. So, I guess could you give an overview of what is system level synthesis and what role did it play in the development of your framework?
Yeah, so the system level synthesis framework is a way of looking at a system that sort of throws away this distinction between plant and controller. So maybe if we're used to state space methods, we are used to thinking about the plant, which is the original system, and then the controller that we design, and we make that distinction. But as I was referring to earlier, in the brain, for example, there's no such a thing as a plant and then some other part of the brain that's a controller. Like that's not a thing. And again, like this is true in bacteria and many other systems. So then we have to think about these systems as being closed loop from the get-go. And these systems, they already have a closed loop implementation where they're sort of controlling themselves. And so um, those systems benefit from being parameterized with a closed loop parameterization, meaning you look at them as already having a state and already having an internal input. And the SLS framework, this system level synthesis framework, it's a mathematical tool that makes that very transparent because we would be parameterizing the maps between the disturbance that hits the system and its state and the disturbance that hits the system and what we would consider to be the control input. And so that makes things very easy, for example, when you want to consider system level type constraints. So for example, in our case with the communication constraints, we don't care about the structure of the controller per se. We care about the structure of the closed loop system. Like I cared about once I have my system in full operation, when I have this fleet of autonomous vehicles like running around or whatever, I want to have the local communication constraints. So you see the constraints appear once I have the full system deployed, meaning the full system running in closed loop. So we want to put constraints at the level of the system. And that is why thinking about the system in this way, as opposed to just the plant or just the controller, is beneficial.
So I guess like the entire concept of system level synthesis is something that I haven't previously come across before reading your work. But it seems really interesting. So I was wondering whether this has any beneficial application in other areas of control apart from distributed systems.
I think so. My focus has been distributed systems, but I know that it's being used for robustness, like for example, for robust MPC, tube MPC. I know Professor Selinger's group in ETH has explored this. Also, Professor Manni at UPenn has explored the robustness against uncertainty and so on with system level synthesis, as well as the connections to RL and learning. So I think that there is a lot of potential applications of SLS beyond distributed systems.
So I went away and did a bit more research into this, and just as an alternative application, I wanted to highlight a paper by Melanie Zeilinger titled Robust Nonlinear Optimal Control via System Level Synthesis. So this paper takes a nonlinear system and then linearizes it around a nominal trajectory, whilst also accounting for the disturbance and linearization error. It then uses tools from system level synthesis to jointly optimize over the trajectory, error feedback, and linearization error bounds in order to reduce the conservativeness of the robust optimization. I also found a very nice kind of tutorial review paper on system level synthesis that was co-authored by John Doyle. It gives a very nice introduction to the mathematical background behind this, and particularly regarding its use in robust and distributed control. Of course, I've left links in the description. I guess moving on to like how this approach can be implemented in practice. So how do you formulate like a possibly very large network of interconnected subsystems and your algorithm in a way that allows distributed optimization to be applied?
So what ends up happening because of the locality constraints is that each subsystem only has to process information from the neighbors, and then they just have to solve a subproblem that is of very reduced dimension because they're only receiving very local information. If they were receiving information from every node in the network, then they would have to solve this big problem but because the information they're receiving is very just constrained to their neighborhood, then computations are pretty fast. So this is how the implementation of the algorithm goes, and this is the reason why it's scalable.
I just wanted to mention here that if you would like to learn in more detail about how this all works, Carmen created a number of YouTube videos towards the end of her PhD that illustrated these concepts in a very intuitive and nice graphical way. I would definitely recommend checking those out if this is something that you would be interested in learning more about. Now, in terms of the algorithm used to implement this distributed localized MPC framework, Carmen made use of an algorithm known as ADMM, or Alternating Direction Method of Multipliers, which is a very common approach to solving distributed optimization. This algorithm builds on the augmented Lagrangian method for solving constrained optimization. This works by first relaxing the system constraints through the introduction of a Lagrange multiplier, known as lambda, and it then iterates between solving the resulting unconstrained optimization for a fixed value of lambda and updating the value of lambda based on the obtained solution. ADMM is very similar, but it splits the optimization for a given value of lambda into two subproblems that are then solved sequentially. I've left a link in the description to a very nice review paper on ADMM if this is something that you'd like to learn more about. Now, in terms of distributed localized MPC in particular, it turns out that you can leverage the sparsity of this problem to allow it to be formulated in a way that ADMM can then be applied, as Carmen now explains.
So it turns out that when you write down the problem as a system-level synthesis problem, the constraints have the right structure so that the problem is partially separable. And what that means is that you can first solve some part of the problem and then solve another part of the problem and try to reach convergence between those two. So you're first solving some subset of the constraints, and then in the next step you're solving the other subset of constraints, and you're iterating so that your solution meets both sets of constraints. And so that is why ADMM is a very useful algorithm in that way, because it lets us iterate between these two sort of subproblems that we're trying to solve. But it did take some time to get it to converge, and it required quite some communication exchanges. So I think we were talking about improving on that. So there is opportunities there if anyone is interested. I know some groups like Professor Anderson in Columbia was exploring extensions of this for perhaps more sophisticated algorithms, but I'm not really familiar with. I haven't pursued that direction myself.
So you've touched already on, or like mentioned very briefly, the data-driven approach. If you've been listening intently, you may realise that in fact nobody has mentioned data-driven implementation up to this point. Yeah, you can blame that on me being overtired and out of practice as a podcast host. So I know there was a chapter in your thesis that focused on data-driven implementation. So why is the data-driven implementation of this framework important or useful?
So a lot of the times when I give presentations about this, I talk about how it's really hard, like how these large-scale networks are just really hard to control with this one controller and so on. And I put the focus there, but then what becomes really apparent is that, well, if they're hard to control, they might also be hard to model, right? And then what makes you think that you'll be able to get this fully accurate model of the system and this very large-scale system, and that's going to be a faithful enough representation that this is enough to control the system? It's often not the case, even if you account for disturbances. So because these systems are hard to model, assuming that you have a model for them, it's perhaps not the best assumption. And in that case, what you can do is you can rely on past trajectories to sort of try to reconstruct that model. Although we don't fully actually reconstruct that model, we directly from the trajectories, we use the trajectories to parameterize what would be the closed loop system response, and then use that to replace the constraint that is represented by a particular model. We instead replace that constraint with the constraints of the system has had this past trajectory, and then one can use Willem's lemma to be able to make the connection and basically solve the optimization problem in a very similar way to how the model-based problem can be solved. Yeah.
If you would like to hear more about Willem's lemma and its use within data-driven control, I made an episode last year with Paula Raposada, who was a PhD student of Willem's and is a co-author on the paper that first presented this lemma. I'll link that below. It goes into a bunch of super interesting background on the kind of key concepts that laid the foundations for data-driven control. So then the final technical concept I wanted to discuss before moving on is the problem of how to efficiently implement this on a GPU. Could you give an overview of how you were able to use the particular structure of your algorithm to kind of make the computations more efficient?
Yeah. I really like this part of the work because it got me into I did this in collaboration with a computer scientist, like a pure CS person, and it got me thinking about algorithms in a different way than how I was used to thinking about them in just a pure control setting. And turns out that when you code up things in GPU, you have bottlenecks that you weren't thinking about, perhaps when you were just thinking about setting up a control problem. And the reason why this algorithm was amenable, like we were able to make this algorithm amenable to GPU, wasn't immediate, but turns out that in GPU you also have this local communication structure. So in GPU you have these threads, and you have many of them that run in parallel. Just as you have in your network, you have a lot of systems that are doing their thing in parallel. But in GPU, these threads, just by the structure of GPU, you can only share local information. Like it's not like every thread communicates to every other thread. And so what turns out that by the way we had posed the optimization problem and we had casted this local communication constraints, the problem was directly amenable to being run in this type of structure. So it's as if, this is not quite accurate, but just to give you an intuition, it's as if each thread were running the process of a subsystem. And so each thread is mimicking the communication with the neighboring subsystems. It's not quite like that because it turns out in GPU, then you have to replicate this the patches of subsystems many times for like a technical reason. And I'll refer people to the paper if they're interested in understanding those details. But I thought it was really cool to see that the constraints that we have in physical systems, and particularly these locality constraints, carry over to the hardware where we actually have to solve these problems. So I don't know, it feels like there's this harmony, right? And like locality constraints are everywhere, and once you have the right algorithms to tackle them, it carries through computation and also practical application.
Okay, so that's kind of all of my technical questions. So then I noticed that during your PhD you did an internship at Tesla. So I was kind of wondering, like, how did you find that experience, and how, like, did that impact any of the work that you've done since?
Yeah, so I remember in my first week at Tesla, they had me give a presentation, and I gave this presentation, and it was very academic. Like, oh, this is why this problem is interesting, and they were like, but where are the results? Like, and that helped me understand how industry has such a different focus than academia, and how results are much more important, and maybe doing things in the principal way that they teach you to do in school is not the priority in industry. So I think that really helped me gain perspective. And although I don't think I'm made for industry as much as I'm made for academia, I think that doing an internship is really valuable in that way, in understanding how different communities face different problems and what solutions could be good enough for one community and not good enough for another one.
So, I understand that you're involved in an NGO and done work as part of that. Could you talk a bit about what that entails, how you first got involved, and I guess why this is something that you're passionate about?
Yeah, so I teach for Clubes de Ciencia, which is this nonprofit that runs in different countries in Latin America, where we go there in the summer and we teach underserved students who are just starting undergrad. And we teach them about our research. So pretty, like we make our research kind of digestible to that level. But I think it's important to expose students to the type of research that is happening in universities and that is sort of advancing knowledge, because a lot of them don't even know what research is or like how knowledge gets created. And they're really, really engaged, and it's really, really beautiful to see them grow through the week that we spend with them, and how they a lot of the times this even shapes their careers. I actually got involved in this because during my time at Caltech, I met some Mexican colleagues that told me that they had applied to grad school because they had attended one of the clubes de ciencia, and someone was an instructor from Caltech and told them about grad school and so on, and that got them into science, and now they had become instructors for this a nonprofit and giving back. So I just thought this was really, really inspiring. I really believe in education empowering people and changing people's lives. So I don't think that my role is just to produce knowledge in elite institutions, but also definitely share this knowledge with the breadth of society, and encourage students to be part of this research process as well. So yeah, I want to use this platform to encourage everyone to check out Clubes de Ciencia, and if they feel like they could enjoy being an instructor, definitely apply.
I have, of course, put links in the description to make it super duper easy for you to check out this program and see if you might want to get involved. Okay, so I've got a few quickfire questions at the end. So firstly, what's the best piece of advice you've ever received?
It was from Terry Sanowski, who is a close collaborator of mine, with whom I have a great relationship. And I remember one time when I was applying to postdocs, I was really stressed out, and I was like, yeah, I don't know if I'm gonna get this position. And he said, Carmen, I've got this advice from an advisor of his. I think it was someone who discovered who coined the word black holes. I don't remember the name of the person, but definitely someone super famous. And he told him, Terry, don't be afraid of making mistakes, but realize them quickly and move on, so that you make progress. And I think I every time I feel regretful or sad about a mistake or I'm let down, I think about that, and I'm like, this is part of the process. I just have to move on quickly. And I find it inspiring with people as famous as this person, or Terry, who's also is also someone really, really famous, give this type of advice, because it shows that it's not just us who struggle. Everybody struggles, and it's really a matter of attitude, of how you deal with it. Yeah.
That's really good advice, I think. What's your favourite part of your job?
Mentoring students, definitely. Working with students, I feel like we are all learning all the time. So I feel like a lot of the times I leave the meetings having learned more. Like the student has taught me more than I've taught them in that one meeting. For sure, this happened many, many times, and I feel like working with students always makes me grow and learn. And also seeing their growth is very, very rewarding. And it gives me this feeling of, we're in this together. We're trying to figure out this problem together. It's a little bit of a team. So I love that. Yeah. That's all of my questions. Yeah, thank you so much for agreeing to this. Thank you so much, Lizzie. So, in summary, distributed and localized MPC is a powerful framework that allows MPC controllers to be applied to large interconnected networks in a way that is computationally tractable and scales nicely with the size of the system. System-level synthesis is an approach to control design that optimizes over the entire closed-loop response rather than just solving for a particular control input, and is useful within the distributed and localized MPC framework for dealing with locality constraints. Industry internships can be a really valuable opportunity to gain insight into different ways of viewing problems, and volunteering for non-profit organisations such as Club de Ciencia
can allow you to have a meaningful impact outside the walls of academia. I really hope you've enjoyed this episode. It was a little bit tricky to schedule, hence why it's a day late being released, but I absolutely love learning about this framework and reading Carmen's fantastic papers in this area. The next episode will of course be part 2 of the discussion, in which I talk with Carmen about her fantastic work on control and AI, so using control theoretic tools to analyse AI architectures, as well as approaches to combining LLMs with more traditional controllers in a way that ensures safety. Very interesting work. That will be released as soon as I finish editing it, so hopefully that will be within the next week or two. Until then, have a wonderful start of the month.